Great. Let's go ahead. Are those scans on? So we have an infinite hollow cylinder. Thickness is T. Radius is R. And R is much, much greater than T. So there's a very small thickness. And current I is flowing on the surface. B is the breaking stress. Find the maximum current so that the cylinder does not crack. Let's try to understand where are you getting the pressure from, and then let's try to calculate it. And others, do keep your cams on. Did you guys figure out why there is a pressure? Think about this thing. All the wires there are parallel, right? And we know when the current is flowing parallel wires, they attract each other. That means if you just choose any one single wire here, and this wire is getting attracted by all of them. So this whole cylinder is trying to compress, isn't it? So that means there is some kind of pressure on the surface, which is trying to compress this whole thing. And so if you apply large enough current, this thing will just collapse. So if I have to ask you, start with this. Find the pressure on the surface. Find the magnetic surface on the, magnetic pressure on the surface. Last time we did for a solid cylinder. This is a hollow cylinder. Find the pressure. Start from there. And this, there is a small catch here. So I'll show you something similar for electrostatics also. Start with the pressure. Find the magnetic pressure acting on the surface. And once you get that, then we can get the stress part. Let's get the pressure part. Now, listen. First of all, you need to know the magnetic field on the surface. So, top view. This is important. Huh? This is one thing, you will, if you don't do this, you'll always get an answer. You'll get a difference of 2. So if you look at the top view here, we know from Ampere's law, we can calculate field inside is 0 and the field outside tangential will be B is equal to mu naught I by 2 pi capital R. Right. So now if you take a small gap here, so I can treat this thing as a sphere plus a small gap, and this is the top view. Okay, we are just seeing this. Meaning, just to look at this, it looks like there is one small wire here and all these wires are present here. The current is coming out of the plane. So we got a gap there. So now look at the idea there. So due to this one, the magnetic field here will be something, let's say B1. Here also it will be almost B1. Now we are taking a point very close to the hole, just inside and just outside. Whereas for this guy, here it will be B2 and here it will be B2. Can you see? Both are opposite. So now if you have chosen the point here, so if I call this point as A and if I call this point as 1 and maybe I'll just call this point as P, and if I call this point as Q, so we can clearly see the field at Q must be nothing but B1 minus B2, but I know this is 0. That means, think about this thing. The magnetic field generated by all these wires is equal to the magnetic field generated by this small segment. And that is the reason the whole field is becoming 0, isn't it? The moment you place that small segment, the field inside is becoming 0. That means all those wires, whatever they are creating, that must be equal to this created by this small section there. And we also know the field at point P is B1 plus B2 is equal to that mu naught I by 2 pi R. So there. So we get B1 is equal to B2 is equal to mu naught I by 4 pi R. Now, why this is important? Now, what we are trying to find here, we are trying to find the force on that small segment, isn't it? Now, force on the small segment will be what? I into L into B due to the remaining wires, isn't it? You cannot take the magnetic field due to yourself on your own wire. Is that making sense? You get in the problem there? So now if you look at that side view, so we are looking at a small piece like this. So this is the small piece we are talking about. So for this small piece here, the current will be how much? Capital I by 2 pi R into R d theta. This is the small current which is flowing in that wire, right? Let the length be L, and this would be your R d theta, right? And here the magnetic field will be B. This is due to the remaining cylinder. So you cannot take the magnetic field due to yourself. This is mu naught I by 4 pi R. In case of a solid objects, you know what happens? Even there, technically, we should do that, but this segment is so small compared to everything, it's almost negligible. But in case of a hollow spheres, it doesn't work that way. It is equal 50%. So the force on this small strip is current L B. Now look at this thing. Current is going up. B is this way, and so the force will be which way? The force will be inwards. I hope you can see that IL cross B, the force is acting inwards. So current will be I d theta by 2 pi. Length is L and the magnetic field is mu naught I by 4 pi R. The pressure will be force on the strip by that area, which is L into R d theta. So that thing comes out to be mu naught I square by 8 pi square R square, multiply and divide by R and send the delta that R. This is the magnetic pressure on the surface. Are you clear with this? If you have taken the full magnetic field, you'll get a 4 there. And there's a very beautiful way to write this answer. You can also write this thing as 1 by 2 mu naught B surface square. Where this is the net field, okay? So B surface is mu naught I by 2 pi R. So if you substitute that, you actually get the same answer. And do you remember what is this formula? magnetic energy density. So that is the easiest way to remember this, right? Can you find the stress now? Get that? I got you the pressure. Just give me a minute. Right. So that is the thing. And just I'll explain you one more thing. So if you do the same thing for electrostatic pressure, hollow sphere sigma. So be careful. Huh? Last time what we did was for solid spheres. We didn't do for hollow. Electro. Here also, no, we do the same thing. We will say we will take a small strip here. We will say here the field is sigma by epsilon, which is q by 4 pi r square. Yeah, perfect. And this is E is equal to 0. So we will take a small piece and we will take this small piece and then we will do the same argument here. We will say this is E1, this is E1, this is due to the everyone. This is E2 and this is E2. And you do this, you end up with E1 is equal to E2 is equal to sigma by 2 epsilon. And this will give you the pressure is half epsilon E square. I think it is sigma square by 2 epsilon. That's your electrostatic pressure. So, and luckily if you see the formula, right, this thing looks like electric energy density. So there is no need to remember that. This is how you can, you'll always get an half. If you take the full field, that sigma by epsilon, that 2 will be missing in the answers. So there'll be two options. If at all they ask you, there'll be two options, one with 2 and one without 2. So be careful. Because the field due to that small piece is very big, 50%, you cannot ignore it, right? You cannot take the field due to yourself on your own charge or your own current wire or whatever. This is also your magnetic energy density. So I can even ask in that question also, how much charge can I keep on the shell so that it does not pop? So breaking stress. So once you got the pressure part, now comes the stress thing. No, here the formulas are just working out. Right? It's not valid. This is not valid for solid sphere. This magnetic energy density thing is not valid for solids. It's luckily coming out for the hollow. So don't remember it. It's not a result. If you try to apply the same thing there, you won't get it. That formula looks like magnetic energy density. Clear with this? Now, how do you find the stress part? So again, when you look at the cylinder, top view, so if you take a small segment here, I'm exaggerating the figure here. So this would be pressure into area, and this will be tension, and this will be tension. Remember the circular motion, sir? So we have that small strip here, something like this. So the tension will be acting like this. It's a cylinder, right? We'll take a small angle, d theta. This length was L, and this was R d theta. Remember, this thickness was small t. So then you know the formula 2t sine d theta by 2. This we did in circular motion, and you should know this thing. This keeps coming multiple places. Is equal to the magnetic pressure into that area, L into R d theta. So this, right? We can do multiple ways. This question you can create in different ways. So let me finish off this. So d theta will get it. Then you'll get P into LR. This is your tension. Breaking stress is nothing but tension by area where it is acting. So you should take this area, that black shaded area there, which is L into T. Make sense? So that is the tension you should take. So this thing, when it is trying to pop, the tension is generated tangentially. So you should take the area perpendicular to the, this is the area perpendicular to tension. So be careful. When you took the force pressure into area, you're talking about this area. But when you take the stress ka part, that is a tension into the thickness ka area. Are you clear with this? So this question, how many ways they can ask you? They will say, we have a cylinder which is rotating with omega. Find omega when it pops. So उसमें क्या change होगा? Here, in this case, you will take the centrifugal force, dm omega square r. That's one way to ask, right? Or I can also say, there is a cylinder, inside there is a gas P naught. Find the pressure of the gas when the cylinder pops. Then it will be pressure into area. I can create magnetic pressure. I can create electrostatic pressure. I can create rotation. You're getting it? So the idea is this. This term will keep changing, the right hand side ka term. So we need to get that force ka part from different chapters. Depends on whether you're rotating or electrostatic or magnetic or anything. Clear with this? The same thing for the solid sphere also, right? In this question, so we will take an half shell. Again, I'll give you some thickness and all. यहाँ पे भी idea वही है. So the pressure is acting this way. So the force will be pressure into projected area, P into pi r square. And where is the stress acting here? The stress is acting, on this small cross section here. So this will be the tension. So that tension by area. So here the breaking stress will be tension by 2 pi r into small t. That will be the breaking stress in this case. Clear with this? So if you're taking a sphere, this is the scenario. If you're taking a cylinder, this is the scenario. The element will be a long, thin strip. The side view would look something of this sort. This is the strip we are talking about. Clear with this? So elasticity will be a part of the equation. Getting it? Elasticity won't be the main question here. You need to get that pressure or force or whatever from different chapters, and then we have to put it. Clear with this? Yeah. You can even put a hollow cylinder with charge. So even there you get a electrostatic pressure. So that is one way to handle that. So that is one. So based on this, if I give you one more, let's say we have two concentric spheres. Let's say this is Q1, R1, Q2, R2. Let's say the outer shell ka thickness is T. B is the breaking stress. Right? Can you find the value of, find the minimum thickness so that the shell doesn't crack? Just get me the equations. So we have a Q1 and we have a Q2 concentric. So get the pressure on the outer surface. That's the fastest way. Because if you get the pressure, then you can use the projected area. This thing is the pi r square is the projected area. This is there in fluid mechanics ka notes. In case you have no idea what it is, you should definitely check out the notes. What an important concept. Comes in 5 to 6 different chapters. Projected area and projected length. So that saves you a lot of time. It eliminates integration. So due to this one, here find the field. Let this be E1. KQ1 by 2R KQ by R2 whole square. And due to this, you will take only E2 by 2. Remember? You will not take the field due to yourself. You have to be careful. That is a catch. So whenever you take the field due to your own shell, you can't take the full field. You will take only half of it. So that is half of KQ2 by R2 square. Is that making sense? So on that small thing, this is the field acting on the, this is the net field on that small area. Why half? We take half only because we take the field due to the remaining shell. The inside shell will give full, right? That is not a problem. But the outside shell, you have to remove yourself and you have to get the field due to others on you. I hope that thing is making clear, right? That half ka part white is coming every time. And that's important. Whenever you take that hollow things, right, that half will always come popping up. So we take half since it is due to the remaining shell. Okay, na? Then the pressure will be force, which is E1 plus E2 by 2, that is a field. Charge will be sigma into dA, that is your charge. So that will give you the force by dA, that will be the area, that will give you the pressure. एक बार pressure आ गया, then you can take half shell. And then you will say this pressure is, constant, but it is acting radially. Now be careful here. Don't say force is P into 2 pi R square. All these pressures are acting in different directions. You cannot directly add it. This will be pressure P into the projected area, which is pi R2 square. So what is projected area, in case you don't remember? So it doesn't matter what kind of weird surface you have, right? So if the pressure is constant, you can simply take this area and you can say the force on the curved surface is pressure into this area. You should check out the notes of fluid mechanics there, and then you're done. So the idea is the same there. Then you will take this thickness there. This will give you the tension, and then you'll say breaking stress will be tension by 2 pi R2 into T. From there you get the thickness. Okay with this? So whatever stress you get, that should be less than or equal to B, so that you don't want to break. So that will give you the Tika value. Jainil.
The sigma is due to sigma is the outer shell ka na? So it will be Q2 minus Q1.
Sigma will be Q2 by 4 pi R2 square.
But on the outer surface, charge is Q2 minus Q1. Na?
Q2 minus Q. Why? अरे this is insulators रे.
Oh, so.
ये गॉसला नहीं है. वो अलग था. नहीं, these are insulators. I know what you're saying. If it had been, yeah, then it would have been, but no, that's not the case. That would have actually made your life easy, pata hai? Why? This is Q1 minus Q1. So shielding effect na, field lines won't come out. Then you're simply solving a question where the charge is Q1 plus Q2. No, that would have made your life easy actually. Like you're simply solving a question where the charge is Q1 plus Q2. These are insulated shells, so that you don't have an issue there. All clear with this? Let's do this one. A single layer conducting coil carrying current I is wound with no gap between the edges and turns. The diameter of the cross section is there. So this is actually a solenoid. Matlab, this actual figure is something like this. Single layer conducting coil carrying is wound with a no gap between the edges and turns on a long cylindrical frame. So these are the top ones are the region where the current is entering inside. You are just seeing the cross section. And here the current is coming out from the bottom. No, exam mein to they'll not explain, but yeah, that is the picture actually. The breaking stress of the material of the wire is sigma naught, then choose the correct option. So that. This is based on what I taught you. So you can simply think this is a cylinder. Right, what I taught you just now, right, was this question. Na? We have a cylinder where current was going this way. This is a cylinder where the current is going like this. समझ में आ रहा है ना difference? So elasticity questions, right, an advanced level, yeah, I don't think they'll ask you anything like, only pure elasticity. That, so I don't think will happen. They will mix it up with either SHM, something like this, magnetism, electrostatics, right, or you'll see few more models work, but yeah. But this magnetic pressure, electrostatic pressure, gravitational pressure, this pressure stuff is important. It's a multiple choice question, right? It's like I'll take a cylinder. So the current is coming out like this. So we know the field outside is 0 and the field inside is mu naught Ni. Again, same idea there. So we have this cylinder. We take a thin gap here. Plus, we again take the thin gap here. So the idea is the same here. So the field here will be something like B1, B1. This would be like B2 and B2. So you'll end up with B1 is equal to B2 is equal to mu naught Ni by 2. So this thing will generally always happen, whenever you have 0 one side and another side is mu naught Ni. So even if you take a small segment, getting at the picture, I'm just drawing it randomly, but I hope you got the point there. It will be half of the field. So that all the remaining solenoid on this small strip will be giving you a field of mu naught Ni by 2. Idea is the same. So now once you got the strip, then how do you get this thing? Then we need to get the force on this thing. So we will take a small strip here. Maybe I'll just draw the side view. There we are taking this small strip here. This is d theta. This is r. Again, you'll get that same stuff there. D theta, we get tension. How is the current flowing here? The current is flowing this way. The current I is this way. And how is the magnetic field? Magnetic field is along the cylinder, right? So B is this way. So IL cross B, yeah, you can take it down or up or however you want. I'll just take B this way. So force would be upward. You're getting the picture there? So then same story again. Then 2t sine d theta by 2 is equal to current I, right? Length is L and that is B. I is how much? I is I only. It's the same amount of current which is flowing through each wire there. Length is L and P will be how much? And which length should you take here? You should take the length along the wire. Huh? This thing will be R d theta. Then you'll get tension is equal to I into R into B will be mu naught Ni by 2. But we still didn't find N. What is N? Small n. So in a solenoid, if you remember, what is small n? N is the number of turns per unit length. And he said the diameter of the wire is small d. That means if you look at the wire here, in a thickness of d, there is a 1 turn, isn't it? 1 turn is in thickness of diameter d. So therefore, the number of turns per unit length is 1 by d. Making sense? That's where you get that n from. So you can substitute here. This will be I square R mu naught N is 1 by d by 2d. Mu naught I square R, mu naught I square R, 2d. First option. वो 2 important है. See, देखा? इसमें 2 नहीं है. इसमें भी देखो 2 और 4. That 2 will be always a trap. When you're taking hollow stuff, that 2 will always come. And then when it will rupture, tension आ गया ना? So then you can find the stress there. क्या दिया? Sigma naught, and that will be tension by area. Which area you will take again? You will take this area. This is where the stress is acting. That would be L into thickness is given. I think that is D, right? Diameter of the wire. Yeah, that will be the diameter of the wire, the thickness of the wire. You can substitute there. I think mu naught I R square 2D you will get. So C option. A and C. Actually, if you got A, I think I would have guessed C and I would have gone ahead. I used to do such kind of things when I was writing the exam in 12th. I mean, it's clear, right? If this was the option, this was the answer. If this was the option, this was the answer. Something like that it is looking. So maybe. Yeah, to check. Maybe I would have been wrong, I guess. No, I would have marked this and I would have marked this. Then I would have gone wrong, which is a bad idea. I should have solved it. Anyways, but got the idea there? I hope this magnetic pressure, electrostatic pressure, elasticity based question, समझ में आ रहा है ना? Solenoid. I hope you can see how things are all getting connected. So make sure to go through this stuff once, okay? Be careful with that solid ka pressures and this thing. So once you got the pressure, you can bring your whole mechanics into it, depending on what you're bringing there. So that is one. And next thing, Ampere's law. Now, we know this is a formula integral B dot dl is equal to mu naught I crossing. But if you have gone through the class notes, I have given you a more general formula. What if it is not a closed loop? This derivation is important. So let's say we got a wire. This is a current wire. And let's say we have a random loop, some random thing. And you want to find integral B dot dl on this curve. And let's say this angle is theta. So this is not a complete closed loop. If it is a complete closed loop, your life would have been easy. You could have said it. Now what we do here, again, polar coordinates. When you choose an element here, so you can choose the elements as a dr, and this is a tangential element, which is r d theta, theta cap. Just like, you have a vector. So here the element dl bar. So if this is an element dl bar, you can write this in terms of dx I cap, dy j cap. This is our Cartesian coordinates. In polar coordinates, you can also write this thing as dr r cap, the radial direction, plus r d theta cap. This is the tangential direction. So you can resolve. So in a polar coordinate, the world will look like this: circles and radial direction, right? So, and here the magnetic field due to the wire will be mu naught I by 2 pi r, and we know the field is always radial direction. So now when you try to use the Ampere's law, integral b dot dl from a to b, this would be mu naught I 2 pi r. Remember, it's a dot product, so theta and r are perpendicular. So theta cap dot r cap is 0. You will end up with r d theta, and if you observe something here, r gets cancelled. You end up with mu naught I by 2 pi integral d theta. So the formula is mu naught I by theta by 2 pi. It doesn't matter what is the shape of the wire. It only depends on the angle subtended between the two corners to the wire. If it is a closed loop, it would be theta is equal to 2 pi. Right? So suppose if you have a loop like this, and then if your wire is here outside completely, now what would have happened? Now if you take something like this, so when you go from A to B in this direction, you're going in this direction, theta. When you come from B to A in this direction, you're covering the angle minus theta. That is the reason if there's a wire outside, integral b dot dl will be 0. You're getting it? When you go from A to B, you're turning in one direction. When you're coming from B to A, you're turning in the other direction. So the angle net will become 0. Right? But if you have a loop here and the wire is inside, yeah, then it is obvious you're always turning in one direction. So 2 pi. That is where you get your Ampere's loop law. Integral b dot dl is equal to mu naught I. Clear with this? So if I give you something like that, you can just use this and finish it up. It doesn't matter what is the shape of the wire. It only depends on the angles there. So based on this, right, you can also have a question also. If you have a current, I, and if you have another current carrying wire I, right? So if this is R1 and this is R2, we use the same logic there. So force will be integral I dl. dl can be written as dr r cap plus r d theta theta cap cross the magnetic field will be mu naught I by 2 pi r theta cap. Same stuff. So theta cap cross theta cap is 0, and r cap cross theta cap will be k cap out of the plane, or minus k cap depending on how you want to take. In this scenario, it is minus k cap. Okay. So you'll get I integral mu naught I by 2 pi dr by r. So this would be mu naught I by 2 pi ln rv by ra. This is the force between a wire and another wire here. Again, it doesn't depend upon the shape of the wire. You can take any random shape. It only depends on the initial and the final distance between them. This is a wire. This is a wire. Clear with this? So polar coordinates will help you a lot there. So this is the force between the wires. You know the force between parallel wires, but these forces are, one is into the plane and one is in the plane. So this integration will be quite useful. And remember this, again, we will use this in work power energy. So you will see questions of this sort. Yeah, I already marked the answers, but you can just have a look at this. So they'll give something like this, some random wire, and they'll ask you P1 to P2. So this is P1, P2, P3, and P4, P5. Have a look at this. I'll give you a minute and then I'll go ahead. You can do it. You just need to get the angles. If I have to show one P1, P2, this is P1, this is P2, draw the angles here. Get this angle theta. You're done, isn't it? और कुछ नहीं करना मतलब you don't care, like you want P2 P3, draw an angle from P2 P3 to the wire and you're done. Just get the angles and you'll get it. 9 mu naught by 24. So you need to get this and this angle. So yeah, it's a little geometry. You can check it out. Right. So give it a try again later on. I will leave it to you. And there's this one more question. It is there in that last time which I gave you the additional equations. This is also based on that only. And in the class notes, check it out. We did 1 or 2 models on this with an infinite wires and all that stuff. So yeah, there are 2 answers because theta, you can get 2 possibilities. Idea is the same. Yeah, you should definitely check out these questions. Have a look at this. Just tell it to yourself, oh, this is how I will do the question. And maybe after the class, you can try. So you can actually do this without even knowing the Arca stuff, This is how you'll argue. You will say, assume there is an imaginary loop like this. Okay, imagine a loop like this. Now, the magnetic field here will be in which direction? It will be always tangential. That means for these 2 wires, the magnetic field will be perpendicular. So integral B dot dl, right, from O to A is 0 because B is perpendicular to dl. And integral O to B is also 0 because B is perpendicular to L. That means integral B dot dl in the whole loop is nothing but integral B dot dl from A to B, isn't it? So integral B dot dl for the loop, right, which is OABO is same as integral B dot dl B to A, and which will be nothing but the mu naught I crossing. So somehow you need to get this angle and then you need to find the current in this Pisaka section. Making sense? So even if you don't know anything, what I taught you, you can do this. But if you remember, you will simply say, I will just join the 2 corners and I'll finish it off. Is the idea clear, everyone? So you can play like that. And this is a pretty good idea. We will again explore this in EMI also. I will give a rod like this AB, and then I will say there's a magnetic field. There I'll ask you find the EMF across AB. Find the potential difference across A and B, the 2 ends of the rod. So that would be an EMI equation. That was one. There is one more small concept. Not a tough one, but let's see. I wrote the answer, but yeah, give it a try. You will get something like sine theta. If I get half, means what? Theta can be 30 or 150. So that dimensions are given in such a way, there are 2 possible angles. So you can check it out. Geometry when you do now, sides are given, 2 sides are given, 1 angle is given. You'll actually get 2 possible angles there. That's where you'll get 2 answers. Do you guys remember that formula? Magnetic moment mu bar is equal to Q by 2m L bar. So you have to be careful with this. So when you read mu is equal to Q by 2m L bar, right? What are you talking about exactly here? So in this scenario, when this rod is rotating, look at the charged particles. The charged particles are going in this circles. So if you look at this, the magnetic moment will be mu bar in this direction. But when the rod is going here, if you look at the angular momentum for the particle, this is your R bar. This is your V bar. L bar is this way, isn't it? The angular momentum of the rod is that way, mu bar is this way. So when you write that formula, the formula is valid. But the thing is that L bar should be in the direction of mu bar. You're getting it? So it was a tough question. So the main idea here is the angular momentum L bar is this way. This angle was 30. This angle was 60. So when you resolve the component in this direction, this will be L cos 60. So then the formula will be mu bar is equal to Q by 2m. This is L cos 60. So QL by mu m will be 4. So that L bar should be in the direction of the mu bar. So be careful. And again, remember this formula is valid only for uniform distribution of charge and uniform distribution of mass. Right? So if the charge is not uniformly distributed, you cannot use this concept. So this thing was derived for that condition. So this is valid for uniform. Both should be uniform. Right? And the mu bar is L bar should be along mu bar. L bar is a component along mu bar. Not a tough question, but conceptual thing. So if you just put directly L, then you'll mess up. Clear with this? Next thing. So we have a particle here, charge q, mass m. It's given velocity v naught. There is a magnetic field in the region B, and there is also a viscous force is equal to minus bv bar. The viscous force will be always opposite to the velocity. So this particle moves, and finally stops because of viscosity. Find the final coordinates of the particle. So as this is moving, the viscous force will keep on dragging it, and eventually it stops. Find the x and y coordinate of this particle there. Viscous force and magnetic force. So think. Take 2 minutes. There's an interesting idea there, which you're going to use again later on in work power energy also. Try for 2 minutes. Let's see. Now, one general thing, right? Whenever you deal with viscosity, that BB bar, and they start asking you for coordinates or velocity as function of time or anything like this is a common theme. Meaning, if you guys remember, last class also was telling you something. That magnetic force equation mein dekha. Since we don't know how to start, we started like this. Let the velocity be Vx I cap plus Vy j cap. Because see, you don't know how the velocity is. You don't know what the hell is happening. So you start with velocity at some point. You start with that. So let the velocity be v bar be Vx I cap plus Vy j cap. So then the net force acting on this particle will be, there are two forces here, Q V cross B, right, minus B V bar. That's your net force acting on it, magnetic force plus this thing. This is nothing but mass into acceleration. So now this is the trick here, okay? Now if I do integral V dt, so if I just put dt on both sides, this will be Q V bar dt cross B bar minus V bar dt is equal to M A bar dt. And now if I put an integral on both the sides, so Q V bar dt cross B bar minus B integral V bar dt is equal to M integral V bar dt. What is V dt? Displacement. So this Q will be displacement. I'll just call it maybe S bar cross B bar. This will be also displacement. What will be this thing? This will be, sorry, A dt. What is acceleration into time? Change in velocity. This will be M del T V bar. Makes sense. Right? And then this thing, so this S bar is what? So if you take eventually, right? So this particle ka motion, if you actually observe, this guy goes like this and it will do something of this sort. And what you're finding from here to here, this will be your S bar, so which is your xi cap plus yj cap. You could have actually substituted Vx, Vy and integrated also. That also would have worked, but this would be more simpler, right? And then, so this would be xi cap plus yj cap cross B bar will be bk cap minus B, S bar is again xi cap plus yj cap. And what is the velocity? Final velocity is 0. You come to rest. And your initial velocity is 0 minus V naught j cap. Perfect. And you just do the cross product here. This will be QXB I cross K is minus J, and this will be QYB cross K is I cap minus BX I cap minus BY J cap is equal to minus MV naught J cap. Bring all I caps and J caps to one side, and then all I caps ka coefficient must be 0, all J cap coefficients must be 0, right? So we will get I caps are how many are there? 2 are there. So QYB minus BX I cap plus MV naught QXB minus BY J cap. So this is equal to 0 I cap plus 0 J cap. Two equations, two unknowns. So you'll get X and Y from here. So this was the trick there. Multiply the whole thing with dt. And again, this trick will work only because your final velocity is 0. Because it is going to stop, because the viscous force will eventually stop you. You can't keep moving, right, forever. Yeah, it might take infinite time, but it will stop. Getting if that was not 0, then you would have got stuck here. If you don't know your final velocity, you can't solve the problem. Clear with this? If at all they ask you find the velocity as function of the position, then this would have given you v final here, and this would have given you x and y I cap. So that you could have still done. They could ask you something like this: find the velocity when the particle is at x comma y. That would have worked out. Then you would have got v final. Is this thing clear, everyone? And let the final displacement be xi cap plus phi j cap. This is your S final. So yeah. So I will leave one question similar to this. You guys give it a try. It's exactly the same thing, but little more here and there data. You can go through the question once. It is the same thing, but there is a little more there. You can try it later on. Answers are matched anyway. Just take 2 minutes, read the question, try to understand, figure it out like how will you solve. Mm, got the idea? I hope you can see the similarities, right? So the question has two parts. First time when you're going in a straight line, you have to solve and get S1 from there, which comes from direct integration. Second case is the same question what we did, and then yeah, you can figure out the stuff. It is the same thing there. So there are two answers. So a similar equation. Let's say we have a tall building. We have slowly entered into viscosity and stuff. So we have a particle here, mass m, projected with speed u. Gravity is present, and the viscous force, let's say, is minus bv. It's a tall building, so this thing will start going something like this, right? Find x and y as function of time t. You get pretty good results there. They can ask you, if it's a very tall building, find the range. Building is very tall, it will land on the ground somewhere, find the range, find the final velocity. Um, yeah, you can ask, find the final velocity, find the final. These are two questions you could ask. This is kinematics plus viscosity. Yeah, I think we'll just do it here only instead of a separate chapter. So there is a magnetic force, viscous force. This is a magnetic force and gravity, viscous force and gravity. This is a projectile motion, particle thrown from a building horizontally. Like I said, start with this. Let the velocity be vx I cap, vy j cap. Start from there. There is brute force integration after that. Let's see. Again, this is f is equal to, we have minus mg j cap minus b vx I cap plus vy j cap. So what I will do now, I'll take down as y axis. I take the horizontal as x axis, just like that. Then I think then this also will become a plus sign actually. So at any point here, if you look at the forces acting on this, there will be an mg here and there'll be a viscous force here, kv. Something of this sort. So kv का component vx I cap, vy j cap. This is equal to m into ax I cap plus ay j cap. So ax will be minus bvx by m. Ay will be g minus bvy by m. And this was easy integration, right? So we can integrate this. You'll end up with vx is equal to dv by dx. Initial speed vx is vu, so u into e power minus bt by m. Integrate this again, you'll end up with the next coordinate, which will be mu by b into 1 e power minus bt by m. I guess, check your calculations. I could be wrong somewhere. I'm just skipping steps. And this thing again, we have to integrate. So this dy by g minus b vy by m integral is equal to dt. Integrate this, this will give you vy. Integrate this will give you y coordinate. But one thing, if you observe here, right, eventually at infinity, vx will become 0 and vy, ay will be 0, right, because it will start going terminal velocity. Vy becomes mg by b. That's your final speed. And also at infinity, if you observe here, the x coordinate will tend to mu by b. Means no matter what you do, no matter whatever is the height of the building, you cannot cross this x coordinate. So if you look at the whole trajectory, right, it looks something of this sort. So there is a particular line here. If you take this as x is equal to 0, this is x is equal to mg by b. And this particle, as it gets closer and closer, it gets closer to the line, but it will never touch the line. So this is your range. That means when you're throwing stones from a building, right, this thing will just not keep going forever ahead. And eventually at infinity, your speed will become only vy, which is mg by b. At that point, your net acceleration is 0 because the viscous force will start balancing mg. Are you clear with this? So that this is your projectile motion with viscosity. So this is how your x and y coordinates will change, just to long integration. So the main idea is once you got this, it is done. You just have to integrate it twice. Clear with this? That is one more on viscosity there. And if you remember in the beginning, I think in rotation or something, I taught you viscous cake problem. Yeah, the disk is there, liquid is there at the bottom. It's rotating stuff, that thing. We did. We'll see again. I don't know it comes. Let's see one more. Let's start off with something. So we have a big cylinder. One side we have a liquid, rho 1. The other side we have another liquid, rho 2. The liquids are not mixing, right? This whole setup is rotating with omega. This length is L and this length is L. And here on this corner, you kept a ball. It's a small ball. You can ignore the volume. So released from this corner. And the density rho is less than rho 1, less than rho 2. Matlab rho 2 is the densest liquid. Ball is the least dense. Neglect any gravity. Find the maximum speed. Time taken to reach the time taken to come back to the initial position. It again comes back. Max distance in row to liquid. So if you're leaving from this corner, will it go to the other corner? Yeah, let's get this. How is this even moving? Start from there. So I'll just give you one thing in case you didn't realize. So if you go at a distance x, right, at that point, the centrifugal force will be how much? M omega square x. So here, the omega square x, right, is behaving like gravity. So omega square x is your G effective. So this whole container will behave like a situation where the gravity is, away from the center, and it is values omega square x, where x is the distance from the center. So the farther you are, the more acceleration will you experience, more omega square x will experience. Clever? That is the main idea there. And then what will be the forces on the ball? So if you look at the force on the ball, there'll be a bind force, there'll be an mg, g ka place omega square x, and you have an acceleration. Is that making sense? So the reason why will the ball go to the left side is because the bind force is greater than that m omega square x. If your omega square x is acting like gravity and density of the ball is less than rho 1, the bind force will dominate. Why doesn't helium balloon go up? Why doesn't helium balloon go against the gravity? Because the bind force, right, is pushing it upward and the mg is pulling it down. So you have to think of like that. So when you have a rotating cylinder and if you have air bubbles inside, the air bubbles will come to the center. Did you ever see a washing machine when you're washing clothes? Observe karke dekho. All that surf, all that foam will come to the center of the washing machine. So lighter objects will go towards the center. Heavier objects go away from the center. When I say lighter and heavier, we are talking about denser and less denser. Meaning, I'll ask you one question. Listen, this will be a good mains question. If you're sitting in a car with a helium balloon, and if the car starts moving, in which direction will the balloon move? You're sitting in a car with a helium balloon. Car suddenly started accelerating. Which way will the balloon go? In the direction of the car, opposite to the car. So think of like this. If this is the situation, if your car accelerates forward, so for the system here, there'll be a pseudo force ma and there's a gravity mg. This is the direction of net force. That means as long as the car is accelerating, it gives you a feeling in this car, the gravity has become in this direction. This is your G effective. I hope you know this thing. In case you don't know, you should go back to the fluid mechanics there. Fluid may we did discuss this. This is the whole concept of G effective here. Where is that? Here, this thing. So when you say down, what is the meaning of down? The direction of net force is taken as down. And this was the whole introduction actually of the chapter also. So you should check out this notes once again there. Right? So So this is down. So that means, so yeah, anyone who's standing here, they will like to stand like this because that is what they will think the world is. So the direction of net force is called down. Perfect. So now if you're hanging a steel ball, metal ball, so the metal ball will go like this because the tensor objects will go that way. If you're hanging a helium balloon, helium will go opposite to gravity. So this helium balloon will become like this. So if you're sitting in a car with a helium balloon, when the car moves forward, the balloon also will go forward. Clear with this? The misconception is this: people think like this, oh, sir, but the pseudo force is acting back on the balloon. True, but there's also buoyant force acting on the balloon. There's a better way to think of like this. Because the pseudo force is acting on the entire air in the compartment, the denser air will go backward, pushing the balloon forward. Making sense? The pseudo force is not acting only on the balloon, it is also acting on the air surrounding the balloon. Because that force is more, all the air will go backside. There is no place there for the balloon to go, so it has to go forward. Making sense? You can figure out like that also. Yeah. So the main question idea is that you can take at a distance x, omega square x, and you can start from there. Now can you try? So at a distance x, we will have a pseudo force. M omega square x. So we can take G effective. So the whole system behaves as if the gravity is omega square x. And then you can just use your regular stuff and start solving. V max is root h1 minus rho by rho omega square L square by 2. That might be right. And I don't remember the answer, but let's try. Now can you write the equation? Write the equation at a distance x. You will see something. Do you guys figure out what it is? It's an SHM. So if you write the forces there at a distance x, so the centrifugal force will be m omega square x, and there will be a buoyant force FB, and I'll take acceleration this way. So FB minus m omega square x is equal to ma. So mass will be density of the ball. Volume I don't know, so I'll take it as V. Omega square x minus buoyant force will be density of the liquid. Volume we don't know. Acceleration is omega square x is equal to mass will be rho V. Acceleration V cancels everywhere, and you'll end up with minus rho L by rho omega square x. That's your, basically this thing is oscillating in SHM there. So this whole term here is your, I'm already using an omega there, so be careful. So I'll just call it omega 1 square. So this is your angular frequency. Right now, since it is starting from rest, that must be the extreme position, isn't it? In an SHM, when it starts from rest, you're at the extreme position. So that is your amplitude there. So on the right hand side, you will go A1 is equal to L. That's your amplitude. And the time taken would be Now on the other side, when you do the same thing, everything will look same. Except that rho 2. So here the equation would be m omega square x minus rho 2 v omega square x is equal to rho v acceleration. This is also rho v. I think you'll get the same equation, but replace that with this. I should have taken it that way. In the direction of x, x is moving that way, right? I wrote reverse. Yeah, माइनस साइन बाहर आएगा, ठीक है. Rho L minus rho minus n. Perfect. So when you solve this, you will get A is equal to rho 2 minus rho by rho omega square x. Yeah, perfect. So the thing is, on both the sides, the omega square is different. This would be omega 2 square. So if you look at the motion here, so from here to here, this is taking t1 by 4. From here to here, now it is not going all the way. This will be something like x is equal to minus 8. It will go to some other distance. This will be t2 by 4. Again, while coming back, it will be t2 by 4, and this will be again t1 by 4. So the time taken to come back will be t1 by 2 plus t2 by 2. It's like two different SHMs on both the sides. They have different frequency. Clear with this? How will you take pressure, right, God? Do you know the area of the ball? So that's how you get the time period. What about the maximum speed? V max will be A1 omega 1 or A2 omega 2. I know A1, which is L. I know omega 1, so I got V max from there. Interestingly, from here you can find A2 also, isn't it? So using this, I can find A2 also. That's the maximum distance it goes on the other side. L omega 1 by omega 2. So you can try and see, when you have no defined thing, a problem when you say ball here, exactly you are taking something like a disk then. Then you have to take like this, ray. See, ऐसा करना पड़ेगा. यहाँ पे you'll take P and here you'll take P plus dP. Then you will say dP into area is equal to mass into acceleration. You can do it, you will get it. Clear with this? That would become complex actually, also pressure and all, but because the thing is you will not understand how to take that m omega square ka term will be a mess. Generally, see, when the objects are, not any defined, not a cylinder or a cube or something, prefer bind force. All clear with this thing. So there, you have fluid mechanics, you have SHM, two beautiful questions, and we have circular motion. You can treat the centrifugal force as that. Take a break, come back by 7:30. We'll continue from here. Any doubts so far? Sure, come back in 8 minutes.
Sir,
बोलो.
सर वो सोलेनॉइड बारे में जो टर्न्स का था वो एक बार एक्सप्लेन कर सकता, वो वन टर्न जो थिकनेस डी में हुआ.
वही है ना, when you keep wires between them, wires ऐसा साइड साइड पे होगा, राइट?
हाँ.
सो इतना, ये लेंथ में कितना वायर था? एक ही वायर था. तो व्हाट इज द डेफिनेशन ऑफ ए नंबर ऑफ टर्न्स पर यूनिट लेंथ? तो इन अ लेंथ ऑफ डी, हाउ मेनी टर्न्स आर देयर? वन टर्न.
अच्छा, ओके.
ना, इफ आई से 2 meters में देयर आर 1000 वायर्स, तो व्हाट विल यू डू? 1000 by 2.
यस.
तो यहाँ पे डी थिकनेस में एक ही वायर है, तो n is 1 by d.
एंड सर वो हाफ जो हमने किया था स्टार्टिंग प्रॉब्लम
हाँ,
पे,
या
वो एक बार एक्सप्लेन कर सकते
if you take a small piece here, we proved that this small piece will also give half of the field as the outside one, isn't it? अगर ये small piece नहीं होता था यहाँ पे, अंदर फील्ड कितना था? जीरो, बाहर कुछ बी था,
हाँ
राइट? नाउ इफ यू टेक दिस स्मॉल पीस, वी प्रूव्ड राइट, अभी वी गॉट ये स्मॉल पीस भी खुद का फील्ड होगा ना, बी वन एंड बी टू, बी वन बी टू एंड बी टू, इट विल पुश ऑन बोथ द साइड्स
यस
tangentially, so it will push on opposite sides. So that means if you take the small piece and if you take the whole piece together, inside is zero, isn't it?
यस
What is the meaning of this? They're equal and opposite inside, and outside they're equal and are in the same direction.
ओके
So both
सो
are contributing half and half ना. अभी देख,
हाँ हाँ
अगर मैंने
समझ
hollow shell दिया charge q, what is the field inside? Zero.
हाँ
इसका
एंड
मतलब क्या था? मैंने अगर इसको ऐसा कट किया, can I argue the field due to the right and left are equal? Symmetry होने की जरूरत नहीं था ना.
हाँ
I can make it even more small na, and now I can argue this small piece and the whole sphere must be equal and opposite inside.
यस
So that means they're giving equal magnitudes outside also.
ओके
So basically we are trying to find the field on the small piece due to the remaining shell. Because when you write the formula F is equal to QE, E is the field due to the remaining charges on nu. E is not the field due to yourself,
हाँ
right? So when you take the force, you cannot take, field on the surface. वो wrong हो जाएगा, because उस field में you're even having the field due to that small piece also.
ओके
वो
ठीक है
लॉजिक था.
सर
ठीक
समझ
है. Look at this. I think this is a PYQ. I think so. I don't remember. Must be. Give it a try. Go through the whole paragraph. Today, the test will be all comprehensions only. Yeah? You have 10 paragraphs. Yeah, writing more than one choice. Paragraphs big work कर लेते हैं इस बार. Next time we will have all matrix matchings. Try. I'll give you 3-4 minutes. It's a good one. I'll just tell you one thing. See, this we did discuss in fluid mechanics. There are times, when your bind force doesn't work. Look at this thing. So normally when you put a block, right, what happens at the bottom of this thing, there are gaps. It's not exactly flat. So there is a liquid under that, and the liquid is pushing in all directions. But somehow, if you actually stick the whole thing to the floor, can you see the second picture here, the right one? If you see there's no space at the bottom, then if you see the liquid is cannot pushing it up, there is no pushing up. Bind force is not applicable here. So a simple way to think of, whenever the lower surface is not covered by the liquid, right? Same liquid, you cannot apply bind force. This is another example here. So we have a container, we have a hole in the container. Someone kept a cone inside, and you blocked the hole. If you look at the picture here, at the bottom, atmosphere is pushing and the liquid is pushing here. So these are the cases, where you cannot apply bind force. You have to solve using pressure. And there was a question like this. There. This is a question. 2006 day I wrote that year. So if you look at this question, right, this is how the picture is. So we have a container. At the bottom, there is a thing like this, and they kept a block on top of it. So if you look at the bottom surface here, look at the FBD here. The liquid is pushing and the atmosphere is also pushing. You cannot apply bind force in these kind of cases. Clear with that? So just keep that in mind. If your entire lower surface is not covered in liquid, you cannot use bind force. Generally, these are the kind of cases you will get. So in this case also, bind force is not applicable. Give it a try. It looks scary. It's not. The only thing is that. Give it a try. Always start with an intermediate position. Let the time be t. Just get the FBD. If you got that, you're done. So if you draw the free body diagram, so from the top, we have rho GH into that area. R naught is the cylinder, pi naught R naught square. And let's say we have glue till here. And he's saying the radius of the glued area of the base varies with time. R is equal to R naught into E naught power kt. So this is some R. So in that area, right, there is no force. So whatever force is there is coming from the side regions here. That would be how much? Rho G. The height of the cylinder is again h there. So 2h. That would be pi r naught square minus pi r square. And we have your mg here. And what is he asking? And there is also normal reaction, right? So there is something holding here, the glue. This is the tension due to the glue. You can just think of the glue is like some kind of a string. So we get tension T will be rho G2H pi R naught square minus R square minus mg minus rho GH pi R naught square. You're done. He's asking when will this become zero? Equated to zero. From there you'll get R. I think that B is the answer. You'll get it. There's nothing there. You just have to solve. And he's asking what? If the tensile strength of the glue is mg by pi r naught square, when it will get detached. So you'll find the tension as function of time t. Pi, the area will be pi into the glue car radius, which is r square. Isn't it? So what is happening here? As the glue is melting, you're getting more and more force. So the tension is also increasing and the area also becoming smaller, isn't it? Both are happening at the same time. Tension is going up in the numerator and the area is decreasing. So when you solve this, that will give you the time. Is that clear, everyone? There is another good way of asking, not the same question, but something similar. Tell me how will you approach this? Imagine we have a cylinder. Right? Let's say it is tied by a string, mass m, radius r. At the bottom, there is a small hole here. And the liquid, right, is seeping in from the sides. So liquid enters inside with speed v. It flows inside and then it leaks out. This radius of the hole is, let's say, a. Meaning if you see the top view, this is the cylinder. The liquid is entering from all directions with speed v naught. So the liquid is going radially and there is a hole there and the liquid falls inside. And let's say the thickness of this thing is some t. ठीक है. Find the tension in the string. And atmosphere pressure is P naught. Just get me the equations. समझ में आया क्वेश्चन क्या हो रहा है? So we have a cylinder and there's a small hole there. The cylinder is on top of that hole. Thickness is T. The distance between that floor and the thing is T. The liquid started entering in all directions and started going inside with V naught. And the hole is A there. You can, then the liquid starts leaving from the hole. So something happens because of the liquid flowing at the bottom. It does something. Find the tension in the string. Or I can simply ask you, find the force due to the liquid at the bottom of the cylinder. That's what I want to know. Did you guys figure out what was happening? As the liquid enters inside, will the velocity remain same? That was the thing. So when the liquid enters here, so this was R and this was T. So liquid here is entering with the speed of V naught. So at a distance R, so when you take a smaller thing, let this distance be X, so this will be T. So now the liquid is entering with some speed V. Equation of continuity. A1 V1 is equal to A2 V2. So this will be 2 pi R T, that is the area of that cross section into V naught, will be 2 pi X into T into V. So we get V is equal to V naught R by X. This is the speed of the liquid as function of X from the center. Means as the liquid is entering inside, the speed is increasing. It's going faster and faster. Clear with that? And now when you apply the Bernoulli, so we'll apply Bernoulli just outside here, 0.1, and we'll apply Bernoulli here at 0.2 at a distance X. Then the equation would be P1 plus rho g H1, they're the same height, plus half rho V1 square. P2 plus rho g H2 plus half rho V2 square. So P1, the pressure is P naught. It's exposed to atmosphere, height is 0, velocity is half rho V square. P2, height is same, this will be half rho V naught square R square by X square. This will give you the P2 ka value. Clear with that? So you will get P2 from here, which will be P naught minus blah blah blah, something like constant type. So P naught plus half rho V naught square 1 minus R square by X square. Yeah. So if you look at that equation, there is a possibility of this value becoming negative, isn't it? There is a possibility of becoming value negative here. When it becomes negative, you know, what does it mean? If this whole value pressure becomes negative, you know what will happen? What does it mean? So I can ask you a question like that also. Matlab, find A before the pressure becomes 0. What do you guys think is the mistake there? See, pressure can't be negative, but why am I getting negative? If the liquid flows faster and faster, right, there is a possibility something of this sort. You have taken that area there. The liquid is flowing so fast, you don't need to flow through the entire area. Are you getting it? The liquid is only entering this part of the area. Making sense? So, matlab area ये 2 pi xt नहीं होगा. It will not occupy the entire height t. Are you getting it? See, I'll give an example. Let's say I have a pipe which is becoming bigger and bigger like this. Now, if I send liquid through this, do you think it will occupy the whole pipe? It will occupy for some time. It will slow down, slow down, slow down. At some point, right, the liquid will start going like this and you'll get a gap at the top, right? You're getting it. So the mistake, right? The reason you're getting negative sign is because you assumed it will occupy the whole space for the entire distance. Are you getting the catch? So there is a possibility that, you know, the liquid, right, is just flowing like this. It is not occupying the whole space. This actually happens with your water taps also. When you open the tap and the tap is becoming bigger, this does not occupy the whole thing. You can't write A1 V1 is equal to A2 V2. Are you clear with this? So there is a limit how much you can occupy the area. So, but anyway, so that is one thing. That is the reason you're getting a negative sign. And then you're done, right? Abhi niche you have to integrate. So this is one way they can play around equation of continuity and viscosity. So upar se P naught into pi r square. This will be mg and this would be P2 into 2 pi x dx. Integral will go from A to R. That's the pressure from the bottom. Clear with this? And that's the tension there. You'll get the tension from here. So the main thing, equation of continuity and Bernoulli. That was the whole idea there. All clear with this? Then that's another good one. So you can play like this. You have a glue. In that case, there is no flow. Here, there is a flow. We have a soap bubble. This we did in the class. Surface tension S, radius R. Inside you have a gas. Eta is the quotient of viscosity. Someone took a pipe here and they placed it here. So we have a pipe, a length L, radius R. Outside of the pressure is P naught. Now, because inside the soap bubble there is an excess pressure, the air will start going through the pipe and start leaking out. Find the radius of the bubble as function of time t. Surface tension and viscosity. So we got a soap bubble. Someone kept a straw of length L inside and left it outside. So the air started leaking through the pipe. Find the radius of the soap bubble at time t. The area will be 2 pi x dx while integrating for net pressure. Yeah, pressure into area, na 2 pi x dx. Na Puroja, what was the doubt?
No, sir, I didn't understand how it was perpendicular. मतलब cross section.
It's pressure, right? Wait, how does pressure act on the surface?
Right, got it.
Do you guys remember which one to use? The moment you see the pipe, you see the length pipe L, radius A, viscosity. There's only one formula which will match that scenario here. Poiseuille's equation. Anyone remember the Poiseuille's equation? Volume per second dV by dt is pi delta P R power 4 by 8 eta L. Poiseuille's equation, in case you don't remember this, you should definitely check out the Viscostica notes. We have derived this also. That derivation itself is a pretty good advanced paragraph. Huh? You should check out the derivation for Poiseuille's equation. This was the derivation there. Page 14, viscosity. Let's see. Hold on. So delta P is your exponential नहीं आएगा रे विहान exponential आएगा क्या? I don't remember. So dV by dt, which is pi, delta P is P naught plus 4s by, let the radius be x, minus P naught. Radius is a power 4 by 8 eta L, and dV is what? Volume will at any instant will be 4 by 3 pi x cube. So dV will be 4 pi x square dx. So substitute there. That's 4 pi x square dx by dt is equal to, we'll put a minus sign because it's reducing. This is pi into 4s by x a power 4 by 8 eta L. Everything is constant there. So this would be x cubed dx is equal to minus blah 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 dt into that constant. Integrate this and you're done. Right? Limits will go from initially r to x, and this limits will go from 0 to t. Exponential कैसा है रे God? Did you take a power 4 को you wrote it as x power 4 क्या? That a is constant, right? Radius of the pipe. Be careful with that. This formula, this r is the radius of the pipe. That is not changing. And not a tough question, but yeah, it's a good one. Surface tension, soap ka thing, and viscosity. You can comment stuff like that. Clear with this? Let's see one more. This is a question from Meredo. So we have an insulated tank. Outside is vacuum, meaning you can take the temperature to be 0 Kelvin. So inside it is filled with a helium gas. Temperature is 1000 Kelvin. Then someone made a small hole here. And the gas started leaking out. So find the speed of the gas when the hole is just made. And neglect any volume flow inside the container, meaning we are not assuming the air is flowing inside. We are assuming it is almost at rest. Only the molecules close by, they are only just leaving. So we can say that is true because you're asking just when the hole is made. If you ask me after time t, we can't do that. Neglect volume flow inside container. So basically, you can assume the velocity of the gas inside is at 0. It's not VRMS. What is the meaning of VRMS? What is the meaning of RMS? Understand the definition of RMS. Just don't stick anything. RMS is what exactly? It is first of all defined for molecules. You are asking for the gas. So the speed of the gas and speed of the molecules is the same. So according to our logic, then the air in your room is actually moving with 3 kilometers per second. No, right? And second thing, what does RMS speed tell you? RMS speed tells you the average kinetic energy of the molecules. If every molecule had that same speed, then the total energy would be same. It does not mean that all the molecules are going with RMS also. This is Bernoulli's equation and thermodynamics combination. In case you forgot, this is something called modified Bernoulli. We did in fluid. Now, Bernoulli's equation, if you see, right, it is based on what? Law of conservation of energy. If you actually go back to the Bernoulli's derivation, you'll realize when you quantity P plus rho g h plus half rho v square, you get one more extra term, which is u by v is constant. So in all the Bernoulli's equation, right, we never cared about the temperature. We always assumed the temperature was constant. So this P, even though it is pressure, it is actually, if you go to the derivation, it is work done by pressure per unit volume. Rho g h is nothing but potential energy per unit volume. So all these are actually energy terms per unit volume. This is kinetic energy per unit volume. Now, we never use this U by V because the temperature of the liquid, we always assume it to be constant. This is your internal energy per unit volume. So when the gas goes from the container to the vacuum, the temperature becomes 0 Kelvin. So what happened to that energy? Even that has to be included in the equation now. End of the day, Bernoulli's equation is nothing but law of conservation of energy. We never cared about temperature because we always assumed temperature was constant. There. So that is how you can modify Bernoulli's equation. So Bernoulli, right, you can actually have multiple modifications also. Like you will find questions like this. There is a pipe here and there is a motor here. The motor is generating power P, find the speed. So you'll enter with V1, but you'll go with V2. So this is generating some more power, or it puts more pressure actually. So you simply say then what? The energy incoming plus power given by the motor is equal to the final energy. So then your equation will be P1 plus rho GH1 plus half rho V1 square plus power per unit volume is equal to P2 plus rho GH2 plus half rho V2 square. So just simply think of it as a work energy theorem. So how do we do this? Get this? I don't remember the answer that we have. Let's see. So that is a catch there. Since the gas is leaking out and the temperature goes from 1000 to 0 Kelvin, what happens to the internal energy of the gas? That also must have gone into something. So Bernoulli's equation now will have 4 terms. So this is your modified Bernoulli's equation. Fluid mechanics and thermodynamics. So we will assume this is 0.1, this is 0.2, just outside and just inside. So now when you write the equation, P, so we are writing this P plus rho GH plus half rho V square plus U by V is constant. Initially pressure will be P, height 0, velocity is 0 because you said neglect the volume flow. What is your internal energy? F by 2 nRT by volume. Finally, when you come out 0 because it is vacuum, height 0, velocity half rho V square, temperature 0. So if you just multiply the volume there, you'll end up with P into volume, F by 2 nRT plus half rho volume V square. P into V is nothing but nRT. So this will be again nRT into 1 plus F by 2. F is 3 for helium. This would be half rho volume V square. Right? So this rho into volume is nothing but mass, but mass can be written as number of moles by molecular weight. So this will be half into number of moles into molecular weight. So this would be nRT 1 plus F by 2. And again will cancel. You get the speed V is equal to 2RT 1 plus F by 2 by molecular weight of the gas car route. So this M is molecular weight. So yeah, gas matters. If it was oxygen, then F would change and molecular weight also would change. This is the speed of the gas just when you make a hole. You can substitute the values there. So 2, Arca value is 8.314, temperature is 1000, and this is 1 plus 3 by 2. Be careful, here molecular should be in kg, so this is 4 into 10 power minus 3. Jainal?
Oh, sorry, sir.
All clear with this? So that was this is actually a question from Meredo, so it's a good one. So you have to use the modified Bernoulli. So the main idea was that Bernoulli's equation, end of the day, fundamentally it is energy conservation. So the question here comes, when the liquid is flowing through a pipe, we never cared about the temperature. We assumed it was always constant. So if it is changing, then what? Let's do one more and then I'll give you a break. This is another thing which we've seen. V is equal to A plus Bx. It's the same question in the notes. Minus By J cap. This is the velocity of the particles on a streamline. Remember, right? What is the streamline? Streamline is the path of the particles. And the velocity of a particles on a streamline is constant with position. Meaning at a given position, all the particles who come to that position will have the same velocity. The particle velocity change with time, but it does not change with position. Can you draw the streamlines? They'll give you 4 pictures and they'll have to fix it. So for x greater than 0. I can ask you find the equation of the streamlines. So in fluid mechanics, if you see, there are three things that you have: streamlines, and then you have equation of continuity and Bernoulli. What was the concept? So if you have a streamline, the velocity of the particles will be tangential. Vx, Vy, and this is angle theta. So tan theta will be Vy by Vx. But we also know tan theta is dy by dx. Thus, that is the idea there. So here, what is Vx? This is minus By by a plus Bx is equal to dy by dx. Thus, shift it, integrate, you're done. So at any instant, if your velocity is Vx and Vy, that will give you the slope, but you also know the slope is dy by dx. That will give you the equation of the streamlines. So if you integrate this, one side you'll get ln y, दूसरा side you'll get 1 by b ln b plus x. I think you'll get ln y into a plus bx is equal to some constant. So you get y is equal to some constant by a plus bx. So hyperbola, right? These are hyperbolas. So c by a plus bx. So if you take for different values of c, if you take c1, so it extends to infinity, y will be 0. At x is equal to 0, y is equal to c by a. So it starts from here. So as you go to infinity, you get closer and closer. So if you go to higher value, so c3 greater than c2 greater than c1. So basically the streamlines are starting on the y-axis and they're going towards the x-axis. Suppose if you take negative values, minus c1, minus c2, minus c3. This is how the streamlines will look. So the streamlines are originating from the y-axis and they're converging on the x-axis at infinity. They get closer and closer, but they'll never intersect. Clear with this? So the picture would look like that. So be careful with that concept. Equation of streamlines there. Okay, take a break. Come back by 8:45. We will start our test. So have your dinner, take a small break. You're tired, 10 minutes, just close your eyes and sit. Learn. This is a practice. Because when you go to the final exam, right, exam gets over at 12 o'clock. But by the time you get out of the center, it will be 12:30. Right? And the exam is at 2:30, but the reporting time is around 1:45. So if you're unlucky, they'll ask you, I think 1:30 only they'll try to come. So 1:45 matlab you will not reach 1:45, na? You'll reach 1:30 only. So you have 12:30 to 1:30, have only 1 hour break in the middle. So during that time, mostly your parents will take you the car and wait for you. And once you come, put you in the car, give you something to eat, and you have to take a nap. You can't sleep, then you have to just close your eyes for 45 minutes. Just close your eyes, that helps a lot. Or else you will get exhausted for the second test. Second paper, you will be slaughtered. Right? So you need to learn how to be calm. No music, nothing. That 45 minutes of silence, you finish eating in 15 minutes. And you need to literally close your eyes and just sit doing nothing. If you do anything else during that time, you'll be exhausted for the second paper. Right? And yeah, you have to be careful what you're going to eat that day.